Hello students, I welcome you in today's session of physics, and in physics you can see here I'm going to take your chapter number 13, which is called as elasticity. Clear? So you can see here this is the chapter and this is the unit of properties of matter. Clear? So before going to start the chapters, just have a look over the syllabus what we have to cover out in this chapter. So in this chapter we have to study about the elastic behavior of solids, then stress strain relationship, Hooke's law, Young modulus, bulk modulus is shear modulus, rigidity, Poisson's ratio, and elasticity energy. Clear? So first we will discuss about the deforming force. You can see here. So the external force which when applied on a body causes any change in its size or shape or both. Clear? Then the force is called the deforming force. Means when you apply a force over a body and this force causes changes in the body, either in its shape or in its size, then the force is called as the deforming force, and the change occurred in the body is called the deformation. Clear? Now come to the elasticity. So what is the elasticity? You know very well, when we apply an external force upon a body, there is a change either in its size or shape or both the body. So this force is called the deforming force. On removing it, some of the bodies again acquire their original shape and sizes. So the property of recovering original shape and size is called the elasticity. And the body in which this property is found is called as the elastic. Clear? So hence you can define it elasticity. Elasticity is that property of the material of a body by virtue of which the body opposes any change in its size, shape or size when deforming force are applied to it, and recovers its original shape as soon as the deforming force are removed. Means if you apply a force over a body, then there is a change in its shape or size, and if you remove the force from the body, then it again acquires its original shape. Now here you can see what is the elastic, plastic and rigid bodies. So first we will discuss about the elastic, plastic and rigid body. So the bodies which recover completely their original state on the removal of the deforming forces are called perfectly elastic, while on the other hand the bodies which do not recover their original state when deforming forces are removed but retain their modified forms are called perfectly plastic. Clear? Here you can see, now moving to this, if on applying the external forces upon a body, the relative position of the particles of the body do not change. That is, there is no change in the shape or size of the body, then such body is called the rigid body. Clear? Now we will talk about what is the limit of elasticity. This is important one. So elastic bodies recover their original state when the deforming forces are removed, but they show the property up to a certain value of the deforming forces. So if we go on increasing the deforming force, then a stage will be reached when on removing the forces the body will not return to its original state. So thus its property of elasticity, you can say it destroy. So the maximum deforming force up to which a body retains its property of elasticity is called the limit of elasticity of the material of the body. Clear? Now we will discuss about, here you can see what is stress and strain. So first we take about stress. When an external force applied to a body changes the size or the shape of the body, then at each cross section of the body an internal reactionary force is developed in the direction which is opposite to the applied forces, and which tends to restore the body to its original state. Clear? So the internal restoring force acting per unit area of the cross section of the deformed body is called its stress. Now clear? Since in equilibrium the restoring force in equal magnitude to the external forces, so the stress is measured by the external forces per unit area of cross section. So you can write it here, stress is equals to force upon area. This is equals to the pressure. You also know that pressure is equals to force by area. Clear? Now we talk about what is the unit of stress. So it's Newton per meter square, and its dimension formula you can see here. Now we will discuss about the bulk modulus of elasticity. So what is the bulk modulus of elasticity? You can see here, this figure is the bulk modulus of elasticity. So when a uniform pressure normal force is applied over the surfaces of a body, you can see here this is a cuboid, and you can see here the pressure is exerted over the surface normally. So what happened? The volume of the body changes, but its shape remains unchanged. So such a strain may appear in all the three states of matter, that is solid, liquid and gas. The change in volume per unit volume of the body is called the volume strain. Clear? And the normal forces which is acting per unit area of the surface pressure is called the normal stress. So within the elastic limit up to which the Hooke's law is applicable, the ratio of normal stress, this is the definition of bulk modulus of elasticity. So you can say that force here is the change in the volume per unit volume of the body is called the volume strain, and the normal force which is acting per unit area of the surface or pressure is called the normal stress. So within the elastic limit up to which Hooke's law is applicable, the ratio of the normal stress to the corresponding volume strain is called the bulk modulus of the material of the body, and it is denoted by capital B. You can see here we denote it like this. Now let us suppose the initial volume of a body will be capital V, now which changes by delta V when a pressure P is applied. Fine. So when the pressure increases, the volume decreases and vice versa. So you can write it normal stress is equals to P and volume strain is the change in volume, that is minus delta V by V. So from this relation you can find write the bulk modulus of elasticity. How much? Bulk modulus is equals to normal stress by volume strain, and you can put the value from this equation, or from here normal stress is equals to P by minus delta V by V and minus PV by delta V. So this is the normal stress. Clear? Now come to the compressibility. So the reciprocal of the bulk modulus of the material of a body is called the compressibility of that material, and it is denoted by beta. So you can see here compressibility is equals beta is equals to 1 by B, that is minus delta V of PV. I hope you understood. Now we'll discuss about what is the modulus of rigidity. So when a body, this is the figure for the modulus of rigidity. When a body is acted upon an external forces tangential to the surface, clear, of the body, the opposite surface being kept fixed, it suffers a change in shape. Means if you apply a force from this direction and there is and the base is fixed at its own position, but there is a change in the upper surfaces, then its volume remaining unchanged, then the body is said to be sheared. So the ratio of the displacement of the layer in the direction of the tangential force and the distance of the layer from the fixed surfaces is called the shearing strain. Clear? And the tangential force which is acting per unit area of the surface is called the shearing stress. So within the elastic limit up to which Hooke's law is applicable, the ratio of the shearing stress to the corresponding shearing strain is called the modulus of rigidity of the material of the body, and it is denoted by neta. This. Fine. So here it is written that you can see here that the demonstration is given here. Let us suppose we are supposing here a cube which is ABCDH IJK from this figure number 4, whose lower surface is fixed. So when a tangential force F is applied at its upper surface, that is ABIH, then what happen? All the layers parallel to the ABIH are displaced in the direction of the force. Clear? The displacement of the layer is proportional to its distance from the fixed surfaces. So the cube, the stake, the new form which is AB A dash B dash C dash E, this form, and the angle theta through which the line AB or BC initially perpendicular to the fixed surfaces is called the angle of shear or shearing strain. So if theta is small, then we can write it like this: theta is equal to tan theta BB dash by BC. Clear? So if capital A be the area of the per surfaces ABIH, so shearing stress how much? Force by area, and the modulus of rigidity of the material we can write it neta is equals to F by A of theta. So here the SI unit of neta, that is the shearing stress, is Newton per meter square, or you can write it Pascal also. Fine, because you know very well the pressure is equals to force upon area, and unit of pressure is how much? That is Pascal, and theta is the dimensionless. So that's why the unit comes out to be Pascal. That is the modulus of rigidity. So dimension is ml inverse t minus 2. Now here you can see this is the determination of the Young modulus of elasticity. With the help of this figure, they are determining the Young modulus of elasticity. What is going on here? They take two identical wires A and B, which is about 3 meter long and about 0.1 mm in thickness or diameter. Clear? So the coefficient of modulus of elasticity is to be determined and taken. These wires are suspended vertically near to each other from the same rigid base. This is the base. So at the lower end of the wire, a main scale S marks in millimeters is attached, and the weight W is suspended from the hooks fixed in the main scale strip. So due to keep the wire taut, A vernier V is attached to the end of the experimental wire B. Here you can see from this figure. The vernier scale is also attached. Fine. So what happened? A vernier V is attached to the end of the experimental wire B and a hanger H is fixed to the vernier strip. So when the weight are placed on the hanger, the length of the experimental wire B increases and the vernier scale V slides down, remaining in contact with the main scale. So by taking the reading of the main scale and the vernier scale before and after attaching the weight on the hanger, the increase in the length of the wire due to the weight placed is determined. Clear? Now we will plotting a graph. So here is a graph between load and elongation in millimeter. That why attaching a load over the base, what is the increase in the length? So that is we are plotting the graph between these two. So a graph is plotted between the load placed on the experimental wire and elongation produced. So this is a straight line passing through the origin. From this graph, elongation, that is L, corresponding to the load M, is determined. Now the radius R of the experimental wire is determined by the screw gauge and the length of the experimental wire is measured using the meter scale. So the value of L, M, R and capital L are put in the formula. So you will get here, this is the Young modulus, which is mgl by pi r square multiplied by small l. Clear? I hope you understood. Now this is the most important one, that is the Poisson's ratio. So what is the Poisson ratio? You can see here. When a material elongated along a certain direction under tensile stress, it contracts along the perpendicular directions. So the fractional change in the direction along which the forces have been applied is called the longitudinal strain. I already told you strain and stress. So while the fractional change in a perpendicular direction is called the lateral strain, the ratio of the lateral strain to the longitudinal strain is called the Poisson's ratio. This is the most important one. Now just have a look over the figure how Poisson's prove this relation. Now the Poisson's ratio is constant for the material of the body. So you can see from this figure number 7, a wire of original length capital L and whose diameter is how much, capital D, is subjected to equal and opposite forces F along its length. You can see from the figure there are the two forces, one is upward direction and one is in the downward direction. So if the length L increases to how much, L plus delta L, and the diameter, that is D, decreases to D minus delta D. So you can write it the longitudinal strain how much, that is change in length by original length, and there is the lateral strain, that is the diameter change. So according to the Poisson's ratio, it is denoted by sigma. The material, the sigma is equals to lateral strain divided by longitudinal strain. So you will get here this relation. Now if the radius of the wire is small r, so you can write it, you know very well, the diameter is half of the radius. The radius is half of the diameter. So you will put this value and finally this expression changes to the radius. Fine. This is relation between the diameter and this is between the radius. I hope you understood. Now come to the work done in stretching the wire. How much work we have to be done to giving the stretching wire or elastic potential energy. So when a wire is stretched, work is done against the interatomic forces and this work is stored in the wire in the form of elastic potential energy. So let us suppose the length of the wire, which is of capital N, and area of cross section is A. So suppose on applying the force F along the length of the wire, the length is increases by x, then the longitudinal stress is equals to force by area and longitudinal strain is x by L. So the Young modulus of the material of the wire is stress upon strain, you know very well, and you finally get the relation FL by AX. Thus the force which is necessary to increase the length of the wire by x is given by YA by L multiplied by x. Now if the wire is further increased by infinitesimal small length, that is dx, then the work done is how much, this is. Using the relation, work done is equals to force multiplied by displacement. Therefore, in increasing the original length from L to L plus L, that is from 0 to L, the work done is how much, you will integrate it and finally you will get the relation. This one, work done is equals to 1 by 2 stress multiplied by strain into the volume of the wire. Clear? Now this work is stored in the wire in the form of its elastic potential energy. So you can write it U is equals to 1 by 2, that is stress multiplied by strain into the volume here. So elastic potential energy, the per unit volume of the sphere, so we can write it like 1 by 2 stress multiplied by strain. But you know very well stress is equals to Young modulus multiply strain. So this relations you can also write it like this: U is equals to 1 by 2 Young modulus, that is the strain square. I hope you understand. Now this is optional, so I am skipping this. And there are the few applications of the elasticity. So let's discuss what are the applications. The first one, rope of a crane. So a crane used for lifting and moving heavy loads from one place to another has a thick metallic rope to which the load is attached. So the rope is pulled by using pulley and motors. Fine. So the required diameter of the rope is decided by the elastic limit of the material of the rope and the load to be lifted. The second one is the design of the bridges. So a bridge should be designed such that under the load of a traffic, its own load and the force of wind, it does not bend too much or break. Now see the third one. So the third one, in estimating the maximum height of a mountain on the earth. So at the base of a mountain, the stress due to the overburdened rock material should be less than the critical shearing stress at which the rock begins to flow. Clear? Now we will talk about the explanation on the basis of the atomic model. So matter, you know very well, is made up of ultra microscopic particle which we call as atom. The atom of a solid are held together in a regular array by electric forces in a way as if they were connected by the spring. You can see this in the below figure, I will show you. So under these forces, a solid remain in natural equilibrium state. Inside a solid, distribution or the positive and negative atomic charges in such that when the solid is in natural equilibrium state, there is no net, here you can see that, forces between the atom. This is the figure, and from this figure I am you can understand what I am teaching you. Now however, the solid is compressed by an external forces, so the distance between the atom decreases. Now the distribution of charges in the atom such changes in such a way that the net force repulsion begin to act between the atoms, and it is called the interatomic forces. So when the external forces is removed, the interatomic forces pushes the atom back to their initial position so that the solid return to its original size. Clear? Similarly, when a solid is stretched by an external force, the interatomic space decreases. In this case, the distribution of the charges in the atom again changes, but now in such a way that there is a net force of attraction between the atom when the external force is removed. The force of attraction between the atoms bring them close to each other to their initial position. Fine. So if the applied external force is very large, so the distance between the atoms increases so much that the net force of attraction between them become negligible. So when this is the case, there is a permanent dislocation of the position of the atom, and on removing the external forces, the solid does not return to its original size. I hope you understand. Now here we are going to discuss, this is the last one. So interatomic force constant. So we have seen that the behavior of solids with respect to the external force in such that as their atoms were connected by the spring. So we know that when a spring is stretched by external forces, the restoring force developed in the spring, which is directly proportional to the k times of x. Clear? So where k is the spring constant, or you can also set it the force constant of the spring. So in a similar way, when the external force is applied on a solid, the distance between its atoms changes. You can see here with this figure. The interatomic forces developed between the atom is directly proportional to the change in the distance, that is delta r, between them. So we can write here F is equals to k times of delta r, where k is your interatomic force constant. Now let us supposing here with L with the length of the wire and RO with the normal distance between the atom of the wire. So we are supposing here when a force is applied, the length of the wire increased by L and the distance between its atoms increases from R to R naught plus delta R. You can see from the figure number 9. So the longitudinal distance comes out to be L by L, or you can write it delta R by R naught. Now since the distance between the two atoms is R naught, there will be on average one chain of atom in the cross section area R naught square of the wire. From this figure you can easily understand, that is there will be 1 by R naught square chains per unit area of cross section. Thus if A be the area of cross section of the wire, it will have A by R naught square chain of atom. Therefore the interatomic forces acting is equals to how much? F R naught square by A, or interatomic force constant you can find from this value. This is this much. Now but you know very well R naught by delta R equals to L by L. So putting this value in equation 2, and finally the interatomic force constants comes out to be this. But force by area, length, Young modulus of the elasticity metal of the wire, we can write it K is equals to Y times of R naught. So the interatomic force constant K is equal to the product of Young modulus of the material of the wire and the normal distance R naught between the atoms of the wire. So this is the end of the chapter, students. I hope what I taught you understand very well. We will meet in our next lecture with a new chapter. Till that, do study. Thank you class. Thank you very much.